Hi everybody, it's Mrs. Dinkelman again. This is Unit 7, Integration by Parts. So this is our first BC topic, I guess. So this integral I have here, x times sine x, is an example of where we would use integration by parts. So if you would, take a pause in the video and just see if you can figure out what that integral is. Perhaps use your calculator and see if you can make a connection about how that integral comes about. So again, hit pause and just kind of see what you would get. So last section we learned or reviewed how to undo the chain rule. That's u substitution. Now how do we undo the product rule? Well, integration by parts sort of undoes the product rule. It's really only if it's in certain forms, and we're not going to be asked to look at the difference between different forms of multiplication and where that rule will be used, but we will have to make a decision about whether the integral should be u sub or if it should be parts. So that's kind of the big thing. So just as a quick reminder, if we remind ourselves a little bit about product rule, once with it's kind of something symbolic because I'm going to show you something here in a second where we'll need that symbolism, and then one with just a derivative. So if I have u times v, the way I'm going to write this is I'd have to do the first times the derivative of the second plus second times the derivative of the first. So for example 1, it's going to be first times the derivative of the second plus second times the derivative of the first. Okay, so as we look through that symbolically, really quickly, so this is what we did with uv prime. So first times derivative of second plus second times derivative of first. This next step is really just isolating this uv prime. So what I've really done is taking this vu prime and moved it over to the other side. So it becomes a subtract. I've rearranged a little bit too. Now I'm going to change those v primes and u primes to dv's and du's, those little differentials like I use with implicit. They really mean the same thing. You might hear my boys in the background, they're playing video games. So now if we take the integral of both sides, so if I integrate here and I integrate this whole side, right? So this becomes our integral of u dv, which we have here. The integral of this derivative should just be itself uv, and then we're going to have the integral of v du. So what's going to happen is we're going to see an integral of this form, and we're going to use this to help us find the answer. And that might seem like, well, you're just kind of flipping variables around, but what we're really trying to do is we're hoping that integral is a lot easier than the original, so we should be able to do it. Now, this is the part that we'll want to remember. You don't really have to know all those steps until we get there or remember why it's true necessarily, as long as we can kind of use it to integrate. What I like to do to remember what's going on here is think of ultraviolet. So this UV that's right here, think of that as ultraviolet, and this part is voodoo. You just have to remember that it's a subtract and then an integral in there. So ultraviolet voodoo. That is not like a mathematically technical way to remember it. So don't write ultraviolet voodoo like on a free response because they're looking for you to be mathematically sound there. So back to that first integral that I had you try. Let's talk about how we would find the antiderivative of x sine x. And I know it's kind of flipped to the next page here, but we're going to go ahead and look and see what's happening here. So with x sine x, so the first thing we're going to do is we're going to choose what u is. So this is just a mnemonic that I like to use to help me figure out which of those things in there should be u. And it's called LIPIT, and that stands for logarithms. So those are our absolute first choice. Inverse trigs, polynomials. I would lump square roots of x and that kind of thing into polynomials. Exponentials like e to the x. That's a really good one to remember. It even kind of looks like it's starting with the word exponential. And then trig is our absolutely last choice for what u would be. So from our example, x sine x, you can see here that I have the x here in the u position, and then sine x is going to be in the dv position. So let me scroll back up just to remind you. Our original integral is going to be in this form, u dv. So what I've just now chosen is what part of my integral is u, and the rest of it has to be this dv. So for x sine x, I decided that u is going to be x, and then dv will be the rest of it. The next thing we need to do is kind of fill in these spaces. So what is du and what is v, okay? So you can see that here on this next step. So when we take the derivative of x, we just get 1. Again, this is more like an implicit here. So the derivative of x would be 1, but we put a dx because we have something with an x. And then here we take the antiderivative. So the antiderivative of sine would be negative cosine. So now it's time to put it back together. So here's our original, the x sine x, and then here's where we do ultraviolet. So this should be u and v kind of smashed together as multiply, minus, and then this is our voodoo smashed together right here. So voodoo gets smashed together. And we can see that there's two negatives there, so that's going to become a positive, and hopefully that integral is a lot easier than our original. So again, we can find the antiderivative of positive cosine, but x sine x, that wasn't so easy. So then we just take the antiderivative. We have that already, negative x cosine x, and the antiderivative of cosine is sine. Just don't forget your plus c. Okay. So let's see if we can replicate that with the next two examples. So again, thinking about Lippitt, okay, we basically here have a polynomial and an exponential. So polynomials take precedence over exponentials. So u is going to be x, and I kind of like to have all this organized here and ready to go. So dv is the rest. That would be e to the 2x dx. So to find du, we just take the derivative of that x, so that's a 1, but we put a dx there. And here we take the antiderivative, so that's going to be e to the stuff divided by the derivative of the stuff. So at this point now, we just put things together. So ultraviolet minus integral of voodoo. So voodoo. Again, hopefully that's an easier integral, and it is because we don't have an extra x in there. So this first part, x e to the 2x over 2, that gets to stay. And let's go ahead and integrate this. So there's already a 1/2 there, and let's think about this. It's going to be e to the stuff divided by the derivative of the stuff, but there's already a 2 down there, so let's make sure it's a 4 now. We multiply that. I put example 3 on here because it has limits. So I just want to show you what that looks like. So remember again, back here thinking about Lippitt, logs are our absolutely first choice. And just by the way, an integral of natural log is one of those integrals that we're going to have to know for the BC exam. So you're either going to want to memorize it or you just do parts like I'm going to do right now. So I'm going to have u equal natural log of x. This one's a little bit interesting because there's not really a whole lot left other than a dx, which is just fine because that makes our antiderivative quite easy. Finding du is just 1 over x dx, so let's do our ultraviolet minus integral of voodoo. So x times 1 over x, well, they cancel each other out, so I just have a dx here. And I'm going to go ahead, I'm not going to put the limits there because I want to make sure that I know that even this thing earlier, I need to make sure the limits are there. So I'm going to do it like this. So I'm going to have x ln x minus x and 1 to e. So again, a quick reminder, if I didn't have these, this is that integral that you're either going to want to memorize, that the integral of natural log of x is x ln x minus x, or you have to know to do the parts like I'm just showing you here. I'm trying to erase. There we go. Okay, so let's go ahead and plug in now. So again, this x ln x, I know it doesn't really feel like I took an antiderivative to get that, but we know that the form works out. So we're going to go ahead and make sure we plug e and 1 into everything here. So if we plug in an e, we're going to get e ln of e minus e, and then minus, and it's going to be 1 ln of 1 times, I better sneak that in there, minus 1. Okay, so ln of e is 1. They're inverse functions, so they cancel each other out, and this is really an e to the 1. So e minus e is 0, and then we're going to have minus. Ln of 1 is 0, and so all we're really going to have is minus a minus 1, so it must be positive 1. So what I would do right now is I would pause the video and I would try numbers 1 through 7 because they're that kind of straightforward type. We're going to talk about next what happens if we have to do integration by parts, perhaps more than one. So that's what the next example is about. So again, try to pause, do 1 through 7, make sure you're confident with those before you keep going here and do example 4. Okay, so for example 4, we might have to use parts more than once. So there's going to be a couple of options here, and I'm going to show you both. So for this first one, let's just pretend like we don't know something weird's going to happen. Polynomials come before exponentials. We just did that one in example 2, I guess it was. Equals. So dv is this e to the x dx. Antiderivative is e to the x. Derivative here, so 2x dx. So when we get to ultraviolet, so ultraviolet minus integral of voodoo. And maybe I should mention here, and I didn't necessarily say it specifically earlier, I know this is not a u sub because x to me would be the inside and the derivative of x is 1, not x. And let me scroll up again and talk about this one. So e to the 2x, the derivative of 2x would be 2, but I have an extra x there. So that's how I know this is not a u sub, because I don't see the derivative there. It's like two things mashed together that don't seem to have anything that they're related in. So with this one, this antiderivative, I still don't know how to do. It is simpler than this earlier one because this was an x squared and this is now an x, so it's gone down by a degree, which means I think if I do it one more time, it will go down by another degree, and that will make that x disappear, and it will make my life a lot easier. So we're just going to do parts on this part here. So I'm going to have u equal 2x and dv equal e to the x dx. So antiderivative is just e to the x. This is going to become a 2 dx. So when I rewrite this, I'm going to make sure I start from the beginning. So we started with x squared e to the x minus. All right, here's my new ultraviolet voodoo. So ultraviolet minus integral of voodoo. And just as I suspected, there's no x there. So I should be able to take this antiderivative. Just because I'm running out of space, I'm going to try to just cut straight to the answer here. So 2x squared e to the x minus 2x e to the x plus, because this minus minus, the antiderivative of 2 e to the x is just 2 e to the x plus c. So simple enough, but what if I have an x cubed there and I have to do it 3 times? So I'm going to show you one more way to get this, and that's using a table. This table doesn't always work. It only works if u is a polynomial. So polynomial, that only works here. So same thing for the decision. X squared, what I'm going to do is I'm going to continue to take the derivative here until I get to a 0. That's why u has to be a polynomial, because I need to know that I can stop my table. So when I get to 0. Here, this is going to be e to the x. Now, what's going to not be so obvious here is that what I really need to do is take the antiderivative here. Okay, it won't be so obvious with this example I picked because both the derivative and the antiderivative of e to the x is e to the x. Now what matches here is the diagonals, because remember it's like ultraviolet. Okay, so I'm going to start drawing the diagonals here. And then notice, because what happens here is we go plus minus plus because of the way this minus sign works in the integral. So plus minus plus. So from this table, what I would say my answer is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Way less work than this, but again, this table only works some of the time. So let me erase and give myself some space here, and we'll do example 5. Let's just use the table. Okay, so remember when you're doing the table, u and dv in there. Okay, so u dv. Okay, so x squared 2x to 0. Remember, we have to have just a polynomial here, so we have to know where to stop at the 0. Cosine. We're taking the antiderivative here. So the antiderivative of cosine is sine, because derivative of sine is cosine. Be careful about the signs, SIG ends here. This is going to be negative cosine for this one, because the derivative of cosine would be negative sine, but that's not negative. Okay, so I think we have the, again, antiderivatives here. We're going to connect these with the diagonals. Maybe it's helpful if I pick different color. Maybe. So those connect, those connect, those connect, and we need plus, minus, plus, minus, plus, minus, however many of those we need, we just alternate that. Now this one's a little interesting because we have minus here, but we also have negatives within our problem. So we'll just have to be careful about that. So my answer to this problem is going to be x squared sine x minus, nope, plus because of that double negative, 2x cosine x minus 2 sine x plus c. Okay, on that one. Okay, there's one more type of problem. I don't know why I have an extra space in that page, but and there's just another example if you want to do the table. I just wanted to make sure that you had another example in there. So, and yeah, let's go ahead and do this one with the table too. I don't know why I put them in both locations. I just couldn't help myself from showing you the table earlier. Let's do another example, which is fine. Oops, this is DB. Okay. So x cubed, 3x squared, 6x, 6, 0. Really nice for these because, again, doing it that many times is really difficult. So e to the 4x, we're taking the antiderivative here. So we're going to divide by 4 every time. So divide by 16, 64. Did I really put that many in there? 256. Ooh, it got kind of big. Okay, we'll pretend that says 256. So diagonals, 1, 2, 3, 4, plus, minus, plus, minus. So the answer is x cubed e to the 4x. There is a divide by 4 in there. Let's see, minus 3x squared e to the 4x. And let's see, that's going to be over 16 plus 6x e to the 4x divided by 64. Clearly, we could simplify that one if we wanted. And then negative 6 e to the 4x divided by 256. Okay. So sometimes, this example 7, the last one, we find ourselves in an endless cycle. So I kind of set this one up already. Again, think about Lippitt. Trigs are a last choice. Just by the way, some books show a different mnemonic, which is fine. They all work out just fine. I just find that Lippitt was the one that makes the most sense to me. So e to the x beats out the trig, so that becomes our u. Sine x becomes dv, so we take the antiderivative here, we take the derivative, and we do our ultraviolet voodoo. Now this particular integral does not look any easier to me than that one. Only thing I've done is change from sine to cosine. So it's actually for this reason that if we try parts again, even though it's going to go back to the beginning, it's going to help us solve it. So I don't know if it's maybe more helpful for me to just write, which I'm going to go ahead and do, but I have all of this next thing written. So out of this that I already have typed up, I'm going to go ahead and change these to pluses because I know that's going to happen. And we're going to do ultraviolet voodoo again on that part. So we're going to have u equal e to the x. I don't know if you can hear my boys again in there, having a good time. Okay, so antiderivative and then derivative here. All right, we're going to start from the beginning. So my original integral is e to the x sine x. And then looking at what I got for my first ultraviolet voodoo, so negative e to the x cosine x plus this time, and here's our new ultraviolet. So ultraviolet e to the x sine x minus voodoo, integral of voodoo, so e to the x sine x dx. Okay, so as suspected, I'm basically back at the beginning. I'm going to go ahead and erase these brackets I have here, maybe, because it's a plus sign there and I don't need to worry about distributing. And what I'm going to do, and here's the trick, it feels like a little bit of a math trick, I'm going to add this integral to both sides. So what I really have is this, two of these integrals now. And on the right-hand side, I have negative e to the x cosine x plus e to the x sine x. Well, remember my goal is really just to figure out what this integral is. Well, on the right-hand side, I don't know what it did to me. On the right-hand side there, when I get there, just didn't like this either. Okay, on the right-hand side there, I have no integrals left. So I basically have my answer, except for this integral has a 2 in front of it. So all I really need to do is divide both sides by 2 here, and I have my answer, which feels very tricky because it feels like I didn't do a whole lot. So I claim the answer is, looking back down here, I just need to add really the plus c at the end of that. So negative e to the x cosine x plus e to the x sine x divided by 2 plus c. So that generally happens when we're working with these last two, like if it's an e to the x and a trig, that endless cycle is going to happen just because the derivatives of trigs, like cosine sine, just change back and forth, and an antiderivative, and e to the x also just kind of changes back and forth. It doesn't get simpler. So that'll happen every once in a while. And you can kind of look through my work on that one as well. Okay, so as mentioned last lesson, here's where we have to be really careful about where we use u sub and where we would use parts. So my advice is for u sub, remember what you always see is that the derivative of something is also there. And for parts, it should not be. They should be two things multiplied together that seem unrelated. Or there's a natural log that could be in there. Okay, so again, for the assignment, first few are fairly straightforward, and then there's some that maybe take a little bit more work, or the table, and I believe this number 10 is the one where you get to do that looping one again, so just be careful about that.